Hello and welcome to RF Design Tutorials. This is Tutorial 11 on RF circuit design with custom 3D components. Here is the agenda for this discussion, and it's a pretty interesting topic. A lot of time designers ask how can we do our own custom 3D modeling in case we are not getting the standard values which we need in our circuit design. So how can I overcome all those limitations and still can do our own custom components and use it in our design work. So this video is precisely going to discuss all those tips and tricks. How can you go about doing something very custom? Now, before we start, subscribe to my channel. Once you subscribe, click on the bell icon to make sure all the notifications are enabled. And after you watch the video, don't forget to hit the like button and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, let's go through one point by one in this tutorial and discuss all the practical things which designer might need during their circuit design. To start with, I will go ahead and use this ADS workspace, and this workspace is available on Keysight Knowledge Center. If you are a supported Keysight customer, you can look at the link in the description below this video and go ahead and download this workspace. And as long as you have ADS 2021, you would be able to run simulations as included in this workspace to try it out on your site. So in the first case, we start with nothing very fancy. It's a simple LC filter. And as you can see, I have 3 inductors in series and 2 capacitors with certain values. And once we run the analysis of this schematic, we can see a pretty decent looking low pass filter response, which is what we would like to obtain. Now, if you wish to fabricate PCB, you need to look for these part values from various vendors. And sometime it may happen that the values which you end up getting after your design are not the standard values, and you cannot get it from any manufacturer as off-the-shelf part. So what do you do in that case? Well, in this kind of inductor geometries, it's kind of very simple. We can come up with our own coils, which is going to give us the values we are looking at. Capacitors usually have a large choice available, so these are least of our problems. However, in this tutorial, I also talked about how a typical multi-layer capacitors, or what we call as chip capacitors, can be designed even in a custom manner if you want to, and then use it in your circuit design. At the end of this tutorial, you will have a layout which looks like this, and here you can see we do have 3 custom coils which I have designed and a couple of multi-layer capacitors. And if you zoom in, you can see these are kind of chip capacitors which you buy. However, of course, you can't see things inside, but that's how the parallel plate inside those capacitors are. Depending upon the manufacturer, you will have the appropriate Q factor and the performance specification of that capacitor. Now after we run the simulation, at the end what I will show you, you will get a pretty decent looking low pass filter response, which is going to be very close to what I just showed you in the schematic. So we'll do all those comparisons as we go along in this tutorial. So stay tuned and let's go ahead and cover each topic by on its own. Now here the point is, this is my final optimized circuit. Now what's my next step? Well, as I just said, next step is to look for the vendor parts which are closer to these values. And in this case, I'm assuming there is no vendor which is giving me this value. And I would like to do my own 3D modeling. As I told in one of the previous videos, if you have ADS 2021, you can download EMPro from the Keysight website and then use it along with ADS. You don't need any special license to run EMPro as long as you have the latest ADS release. It's all included in the product. Now, EMPro is a full 3D modeling platform, pretty much like any other commercial 3D tool. And to do your geometry modeling, there are many ways of doing so. If there is a vendor who's giving you some 3D CAD files, you can go to File, Import, and you can import a CAD file. And EMPro supports variety of 3D CAD file formats and most common being .sat file, but you also have .igs, step, SolidWorks, CATIA, ProE, and all those formats supported. So no matter what format manufacturer or your partner is giving you, you can import the 3D model into EMPro and then assign the right material and use it along with ADS circuit design as you need. The second approach is to do scripting, and EMPro includes Python scripting. And if you know how to do programming in Python, you can program it to create the geometry which you are looking at. And if you refer to help, there is a documentation available to look at a scripting cookbook or the APIs where you get all the Python modules, classes, and everything. So if you know how to work with Python, you should be able to use some of these modules, classes, and functions to come up with your own script to create any 3D model. Well, the third way is obviously the normal way, as every RF designer would do it, is to draw your own custom 3D object. Now, to draw 3D objects in EMPro, you do have a variety of ways. For example, if you look at create geometry, you can use some of these 2D to 3D translation kind of options, or you can use these 3D primitives to come up with your own structure which you're looking at. In my case, the first example I will show you is about making the coil for an inductor. And we will use a 3D primitive here called helix. So once we click on helix, the 3D primitive property box come along, and now you can enter the dimension of the helix as indicated in the picture here. Now the question might be coming to your mind, how do I know which dimension I need to put in? Well, there are many manual calculation methods and also some online calculators, such as the one I'm using here from 66pacific.com, and they have a pretty good coil inductance calculator. You can select the units you want to work with, enter the specification of your coil, and once you hit calculate, you get the inductance calculated here. And as you can see right now, I do have an inductance of 19.5 nanohenry because it's e raised to minus 2 microhenry. So that's 19.5 nanohenry, which is kind of pretty close to what I'm looking at as one of my inductors in circuit design. And I was looking for 18.3. So that's pretty close. So we will use this, and if required, we will do a bit of fine tuning there. So once I know my number of turns, diameter, length, I can come back to EMPro and I can enter those, specifications or values here. Now, once you have in definition properly defined, you can see there is a 3D geometry which EMPro has come up with. And once you change those parameters, this geometry will change. Now notice by default, the helix has been drawn on XY plane, and you can see there is a triad here, and it's actually drawn in a Z axis direction. But think about your PCB. Usually we always commonly refer PCB as XY plane. So I would like this coil to be facing on XY kind of axis. That means I don't want it to be drawn in Z direction. Rather, I would like to be drawn in X axis direction. And for that, what you need to do simply is look for a perpendicular plane. So YZ is the perpendicular plane for X axis. So under specify orientation, you can go ahead and just select a YZ plane. And now notice the coil is actually in the X axis. So once you're happy, you can say done. And now you have a helix model added under the parts, and this is the 3D item which we just created. If you want, you can rename it to whatever name you want to call it with. Now, another thing you notice, ultimately we need to place this coil on the PCB in the X orientation here. So that means this helix, while it is forming the basic coil, but I still need to extend this to X axis and then attach the mounting pad, which we will solder it on the PCB. So this model is not fully complete, it's little incomplete. Now another thing you notice when I look at X and Y and keep the Z axis on the top, the coil is ending here and this side is ending here. In reality, I would have hoped this coil to be moved like this. That means I would like a 90-degree rotation. As you can see, now I'm looking at y-axis, which is at 90 degree to z. So I would like to, rotate this coil by 90 degree, and I could have done that while I was creating the coil, but then it wouldn't have, made it very clear to you why am I doing that. So now once you know that, there are two ways we can go back. You can see EMPro keeps track history, keep track of the entire history of your component creation. I can go back and double click on this primitive. And while we are in this orientation, I could rotate it. So U represent X, V represent Y, and W represents Z axis. So I can go ahead and rotate it along the W axis and enter the rotation degree as 90. Now what you will notice here, the coil is actually this, two segments here or two ends is facing down. And once I click done, you probably can see that. Now the coil is properly positioned, the ends are properly positioned. And now only thing I need to do is to extend these branches, beyond a certain point, and then put the mounting lug or the mounting, kind of pad here. And that can be very simply done using a command here called extrude from face. So I will select this option. It asks me to select a face. I will go ahead and select this face. You can see it's kind of highlighted. And once I go to extrude option here, here is your extrude with some default number. So let me enter 0.4 mm so that this branch goes slightly below than this coil. And I'm happy with this. Click done. And now you can see I have added this branch here, and there is a new model in the tree here. And that model is the default name, and that's representing this branch. Similarly, on the other hand side is pretty simple. I will go ahead and extrude it from face, select that particular face here of the coil, and in extrude I will again use the 0.4 mm as I used before. And once we say done, now this coil looks pretty okay. Right, and now you can see there's another model. Now the only thing remaining for us is to put the mounting pad so that it looks like some coil which I'm really going to solder on the PCB. Now to model the box, again I can use a 3D box primitive and I can enter the dimension of the box as I'm looking at. But let me show you another way of doing 3D modeling, and that is to use this 2D to 3D translation kind of command. Now here, if I select extrude, what this means basically, you need to draw the face of an object and then you can extrude it in any direction, either on x-axis, z-axis, or y-axis, depending upon where you need to expand it. Now, as soon as I go into extrude, you can see a cross section, and here is your drawing axis. And currently, this drawing axis is basically not in the right place. It is going to a global origin here. And I'm not happy because I don't want to draw my box there. And again, there are various ways of doing it. So you can work on a global context or you can work on a reference context. But here I will use local, but I will shift the origin. That means this global triad, which you see, I can shift it below, shift it slightly on the lower side, and that's the z-axis. So I'm going to shift the origin to minus 0.5 so that now you can see the drawing plane is actually below the coil. So now it's a little more comfortable for me to do my mounting lug here or the mounting pad. Right, so once the origin is shifted, I can go back to edit cross section. These are different 2D views from which I can see this coil. Now to get exact idea where is this mounting pad should come to, I can look from the bottom Z direction here so that I can see the lower end of the coil. And now this is one of the segments. I will go ahead and use a rectangle, and I will draw a rectangle which is covering this leg here. And now I can go to extrude, and now you can see it's kind of extruding in a certain direction. And again, I don't want anything in U, which is X, nothing in V, which is Y axis, and I would like it along the Z direction, so I will enter that as 1. 1 indicates in which axis direction would you like to draw it. All right, so now you can see the extrude distance is 0.4 and this is actually too much here. So I'm going to reduce it. Let's try 0.2, and zero point 0.2 is just sufficient because it is covering the helix arm and these two are getting shorted. So I'm pretty happy with that. Click done and now you have that box already defined. Now same thing I need to do for the other side. Now I could use again the same method and draw a new box, but then I want this box and the other box to be precisely the same size. So I'm not going to draw a new box here. I can simply take this model here, right click, go to edit and copy. And now once I copy, I can right click on parts, go to edit and I can paste. Now I have a new model here which is placed right now at the same location. I could right click, select modify, specify orientation. Now when you specify orientation, you can enter a new origin point for that box, or you can simply use this triad and you can shift those box using this triad here. Now, if you don't want to do this movement, there is a shortcut in ADS. So in EMPro, if I see the geometry from the bottom side, here is the tool and I can use match point command here. I simply select the center point of this box and then move my cursor and select the center point. And now you can see those 2 points snap. Now this is placed at the right point. The only thing I need to do here, shift this Z origin back to minus 0.5 as we did earlier. And now once we do that, I have the second mount element. Simple, isn't it? Very, very simple. Any 3D modeling is just knowing your X, Y, and Z and which plane you want to draw and in which plane you want to extrude the geometry. So now I do have my coil as I wanted. But currently you can see EMPro is complaining, saying it doesn't have any material assigned to it because by default it is an unassigned material for the objects which you have been applying. So now under materials, I can right click. I can either add my own material or I can add it from the library. And here we do have large material library in EMPro and you can pick any material of your choice. Now for this coil, I know I'm going to use copper. So we can go ahead and select copper. And now how do I assign this material here? Now before I assign material, all these objects are going to be one single object, which is representing my coil. So instead of keeping them as a separate item, I can select all of them, right click, Boolean, and I can make a union so that all of them are merged together. And now you can see you have a single part. And once you select that part, the entire coil gets selected as I wanted. Now I can simply take this material, drag and drop it to that object. And now you can see the color change, which indicates the material has been aligned, assigned to that. Now, once I select the coil, you can see two ends and the coordinates of those ends. Now, the lower coordinate, if you try to read the C axis, it's minus 0.5. And no surprise, remember when we drew this pad, we shifted the origin here. But now I would like to use this component inside ADS where the reference will start from 0 mm. Otherwise, when you place this component in ADS, you need to remember this offset so that you can cancel out this offset from 0, 0, 0 location. So I don't want to do that because I know this object has to be used in ADS. Why would I like to remember it? So I just want to shift this origin back to 0 in Z direction. So I can simply right click, modify, specify orientation, and now origin. So minus 0.5, and to cancel out, I need to shift this origin in Z plus direction by 0.5. And once I say done, now if I select, you can see it's e raised to minus 16 mm, which represents 0 mm. So now this object has the right origin reference point, and my job is much simpler when I want to use it inside ADS. Now once I'm done, let's save this. And once we save the project, we can select where I would like to save. Now, whenever you want to use the 3D components in ADS, You could save it in any new directory or a library and then add that library into your ADS workspace. However, in this ADS workspace, you can notice inside the workspace at this location, I already have a couple of libraries which I'm using as my design library. So if I save my component directly in one of these libraries, then my job will be much simpler because I don't want to go to design kits, manage library, add a library. All those things will not be required because I'm going to save it directly inside the workspace. But again, choice is yours. If you want to create a separate folder where you want to keep all your 3D components, you can do that. In ADS workspace, then you can go to manage library, select add library and browse to that folder where you have kept all your 3D components. So choice is completely with designer how they want to use it. All right, so in my case, I'm going to save it under the same workspace and mlcc underscore lib. And now let's call it demo underscore coil. And once I save it, it's a EMPro open access project. Save it and my job is done. So I'll keep this open. Let's shift to ADS now and look under folder view. But here I do not see demo underscore coil. Well, the reason for that is this needs to be refreshed. So I can go to file, recent workspace, and I can just simply click on the same workspace where we have been working till now. And now you can see it's refreshed. It's reading the new cell. And under the cell, you do have a EMPro instance, which is basically showing you the picture of this design here. It also has a layout and the footprint. Basically, they are the same thing because different people prefer to use different naming. So we do have both, but both essentially are same thing currently. Now in ADS, I can open up a layout, and in this layout, I can drag and drop this 3D component footprint. Now remember we talked about Z offset, and in case you haven't nullified, this is the place where you can offset Z specification. So if I would have left it like I was doing it before, I would need to enter 0.5 mm at this point here. But right now we already offset that into the 3D component, so I don't need to specify anything. So that's done. So I have one inductor coil placement here. Let's use the con layer and just draw a dummy kind of mounting pad for this inductor. And you can see this symbol here is actually a top view of the inductor showing you some key vertex points here. Now once I have these two conductors, if I look at my stack up, so it's a simple 2-layer PCB stack up using Rogers 4350, and I'm using a bound layer here to constrain the PCB size. So in my layout, I will, from the list of layers here, I can select bound and just draw a dummy PCB size just to satisfy the criteria at this time, because right now this PCB size really doesn't matter. And if I click on RF Pro, basically I can look at how this geometry appears in 3D, whether all the alignments with the con layer and which is what I'm going to use for my EM simulation is correct or not. So here you can see RF Pro, loading the 3D component along with the con pad. And if you notice here, this pad is very nicely aligned on top of PCB. So there is no offset, no error in my modeling, and I can go ahead and use it for my circuit design purpose. So that's one simple way of how to do EMPro 3D modeling and bring over that component into ADS. Now, how do I validate whether this coil is giving me the right results or not? There are a couple of ways again. Again, if you have EMPro and effectively you are going to use FEM simulator inside ADS, and if you already have FEM license, you can also set up a simulation in EMPro, and you can see you do have an FEM simulator here. But again, if you have a full copy of EMPro, you also could have access to FTTD, which is a time domain 3D simulator. So it's a full standalone 3D simulator, simulation kind of software. So you have all those features as you would get in any other 3D tool in the market. So if you want, you can simulate this coil here and then look at the results. But in my case, I would prefer to do a validation in ADS. So here, let's come back to our ADS main workspace. And once you download this workspace from Knowledge Center, you can go and experiment with all these things. So in this folder here is step 2 RF Pro 3D model characterization. You can see here I do have a capacitor model. I do have a bench for inductor model and so on. Now before we go into validation, just for completion's sake, let me show you what 3D models I created using the same process I showed you just now. I do have an air core inductor, which is basically 7 turn. Another one is kind of 10 turn. And I do have this multi-layer, capacitor. And if I just show you how this multi-layer capacitor is drawn, when you are in ADS and you want to open up the 3D editing, of this model, let's say you want to modify something, you can double click on EMPro, click on this icon here called Open in EMPro, and this will automatically launch the tool and load the geometry which you have included in your ADS workspace. So here you can see this is a multi-layer capacitor, which I modeled using similar techniques that I showed you just now, and then I saved that model inside ADS. So these are the 3 models which I'm going to use in my design. And here for each model, as you can see, I have created an RF Pro setup. I have performed a full 3D FEM simulation on individual models so that I know what is data to look for. So in this case, you can see here's a capacitor with a couple of mounting pads. And if you look at my setup, I have 2 ports placed here. And I have run an FEM simulation till 10 gigahertz using the FEM simulator built in. And after simulation runs, and it only takes few seconds, if you see here, to simulate and capacitor, it takes like 30 seconds on my laptop. And once I open up the results here, you can plot either the S parameter or you can switch on capacitance calculation, and here's the capacitance versus frequency. And if I place a marker on this capacitor curve here, and let me change the font size here, let's make it something like 24, and you can see this capacitance is close to 9.7 picofarad at a certain frequency. And again, this value of capacitance will change with respect to frequency, but this is kind of pretty much close. And I can see the resonance happening around 2 gigahertz for this capacitor. Similarly, I do have test benches for inductor, like this inductor is 7 turn. And if I open up RF Pro, it's pretty similar coil to what I just showed you, and it's already been simulated along with 2 mounting pads. So let me directly open the results and show you. So in S parameter, if I switch on S11 and then I use the inductance calculation, here is your inductance curve. And as you can see, it looks like a pretty decent inductance. And if I click anywhere on my graph here, let's make this marker bigger, maybe 24, and you can see it's around 6.2 nanohenry of inductance. And if you remember, in my schematic I was needing 6.2 nanohenry, so this is representing a pretty good inductance value. And similarly, there's a third inductor, and after I perform RF Pro simulation, I created a schematic. And again, how to work with RF Pro, I already created previous tutorial videos on RF Pro, so feel free to go ahead and explore those videos to learn more about RF Pro. So here I have a test bench with all 3 components. Under S parameter, I have switched on Y parameter as well. And once you run simulation, I have few equations on the data display to show you the response. So here is our 7 turn inductor. Here is your 10 turn inductor, and giving you 18.3 nanohenry kind of value. And then you have capacitor, which is giving you 10.1 picofarad at around 530 megahertz. And these are the Q factor curves for inductor. And you can see the Q factor is quite high, giving you a good quality inductor with our custom modeling. Now let's proceed. So that was step 2. I have all my components. I characterize those components. They are meeting the value specification as I was needing. And for each of those components, I have created these model. And basically these models are nothing but the S parameter file generated by RFPro analysis here. All right, so once I have those models, I can go to step number 3, where I'm going to replace each of those IDLLC components with these models. So if I push inside, these models are the same, containing RFPro simulation results. Now, once I have these models, let's go ahead and run simulation. And here on the data display, you can see the blue curve, which is the step number 1. That means results with IDLLC. The red curve is with our 3D components, but right now each of those components are simulated by FEM, but we have used a schematic with an ideal wire correction. So this one is still not containing the PCB parasitics or element to element spacing, kind of coupling between them. But here you can see both S11 and S21 is agreeing very nicely. In fact, our model is giving far more rejection as compared to the earlier filter design which we did. Now, so that satisfies our criteria. That means our model is good, our topology is good, and we can proceed to next stage. Well, step number 4 is to come up with a PCB design. And here is the layout using those components. Now, how do I place these components in the layout? As I showed you earlier, you can pick these models, any one of your choice as you want to place. Drag and drop the layout, and then you can enter any offset or any specification. In case you haven't taken care of orientation, like in this case, you can see originally when I modeled, I thought I will prepare the PCB into this direction, but later I ended up designing PCB in this direction. So this element is not in the right, angle. So I can take this model, just press Ctrl R, rotate it so that I can place it properly. So not a big deal, pretty simple. So all 5 components like X3, X7, X5, X1, X6 are those models which we created using EMPro. And now here is the same, RFPro view, which I showed you at the beginning of this video. And that's including the full loaded PCB and all the components. And again, I have used a bounding area layer where you can see this is the PCB size, which I have defined in the layout using this bound layer onto this particular PCB, the 2-layer PCB we have used in this process. All right, so once we have this RFPro interface and we can see everything is properly connected, I went ahead and set up a simulation from 10 megahertz to 1.5 gigahertz and selected FEM to simulate. And if you look at simulation summary I just ran, it takes around 6 minutes and 37 seconds to run on my laptop, which is very, very respectable. And after I have this filter, if you look at the response, it looks pretty much the low pass filter we were hoping to get. Pretty decent, return loss as well as transmission response. But we will do, comparison with our schematic. Now, while you are in RFPro, another thing which I did while simulating this circuit, I also stored fields on all frequencies. What does this mean? If I store the fields and if I double click on the near field, I will be able to plot E field, H field, or the surface current density across my structure. Now let's say if I want to plot E field for this structure, and let's select a close frequency, to the cutoff, which is 500 megahertz. And then I can select in what all elements or objects I would like to see this. So I'm going to select these things starting with X3. You can see it's selected one coil. And now you can see the E field in that coil, and similarly you can plot H field if you want to do so. So choice is completely yours, and this way I can go ahead and keep selecting all the objects where I am really interested in watching the E field or the representation of the current. So let me go ahead and pick all of them. Now here all of them got selected, and if you want to get a more clear picture, you can right click go to properties on this color density plot, I can switch off the automatic mode and switch it to something like manual mode of my choice, so that you can see some proper current distribution across the structure in terms of E field. If you want to see current field vectors, you can switch on current density, and now you can see the current field vectors across the structure. And the resolution of this current field vector can be controlled by you by going to surface resolution, select extra fine, and now you will see finer current density vectors across the structure. And again, if you want to see the propagation of the field from one port to another, I can go to sequence tab and switch on the sequencing. And the sequence will actually excite one port, and you can see how field vectors are changing once the current is propagating through the structure in your case. So this gives you a lot of design level insight about field distribution and the current propagation through your structure. So let's pause this and let's come back here. So that's one of the additional things you can do. So we'll do unload so that we can unload all the results and get back to our geometry. Now after our simulation is finished, we can double click here and generate a test bench, which in turn will generate a schematic containing a test bench as per your setup in EMPro. So here you can see I have an S parameter simulator set from 100 megahertz to 1.5 gigahertz. This is our overall data which we obtained in EMPro for the full layout. And once we run this analysis, we can compare three graphs here. So the blue graph is our ideal LC. The black graph is when I used EMPro individual component models and used circuit simulation. And the red graph is basically our full 3D simulation of the entire layout along with the PCB parasitics. And you can see in all the cases, my response is very decent and the return loss is very well compared between these two representations. So now I can confidently say that the layout which I was hoping to design is completely done because we ran a full 3D FEM simulation, and we can proceed for Gerber file generation and the coil winding and then assemble our PCB and test it out with network analyzer and then compare the response. Well, hope you liked the content presented. That was all the agenda points which I originally set out to cover in this tutorial. Hope you got a pretty detailed insight into how can you do those custom 3D modeling, bring over those components in ADS and set it up as your circuit design components, and then finally do a complete layout and do a full 3D simulation in EMPro environment. So hope you like the content presented here, and if you do so, don't forget to hit the like button, leave your valuable comments in the comment section below this video, and feel free to download this workspace from our Knowledge Center if you are a supported Keysight customer and try to play with it on your own time. Thanks very much for watching. Wish you all the best with your design work.